Maybe we can begin. Thank you everyone for joining this month's uh, issue, I suppose, of the Canadian Transfusion Trials Group Research Methodology Lecture Series. And we are happy to welcome back Robert Balshaw. Rob is an assistant professor in the College of Community and Global Health and a senior biostatistician in the data science platform of the Gregory and Fahey Center for Healthcare Innovation. He has been a consulting biostatistician for industry, government, and academia for 35 years and has been the lead statistician for dozens of clinical trials and consulted on hundreds of research projects. He gave a really fantastic presentation last year to this group, and we're happy to welcome him back to speak again on statistical considerations when designing your clinical trial. Rob, over to you.
Well, thank you, Jacob. A very kind introduction, and I'll just to make sure, I misspelled biostatistician on my CV for about 20 years, and I just want to check. Did I say the Gregory and Fahey Center for Healthcare Innovation? It's the Georgian Fahey Center for Healthcare Innovation.
I am so sorry. You are correct.
Okay.
It was Georgie. I misread that as Gregory. You have it spelled correctly.
That the error was just as likely to have been mine. So thank you.
Okay.
Um, Also, I'll just say that this talk one, I was glad to hear that it's billed as a lecture, not as a research seminar. Basically, I'm uh, uh, a jack of all trades biostatistician, and my job is to enable clinical trial researchers and other researchers in the medical community to get their work done. Research in the broader sense, I'm part of. I don't really have a research agenda of my own, so you won't be hearing about any wonderful new statistical ideas today. I'm really just talking about things that are happening in the space, and I'm hoping to I don't know, inspire some increased collaborations with clinical trial statisticians and clinical trialists on the clinical side of the house. So for those of you who've deep statistical training, this is going to be a very much preaching to the choir kind of talk. Those of you who are more clinically oriented, again, if you've done lots of clinical trial work and are sort of keeping up with the where things are going, this will be familiar stuff. If you're just starting to get into clinical trial work, then I hope this sort of constitutes a bit of a roadmap for improved trial designs. So yeah, I will endeavor to share my screen now, and that's what I was hoping to share. Don't need that. We don't. Assuming we don't need that. There we go. So. Clicking on the little green button should have been like, there we go. So I'll just say thanks to the invitation to speak. I enjoyed the talk last year. We had some interesting discussion afterwards, and I hope we'll be able to continue that kind of back and forth. Hearing what you guys think about things that are being talked about by a statistician is always interesting for me. So. And I'll just the conventional land acknowledgement, but I thought maybe I just take a moment. I know it's not just a Manitoba, it's not just a Winnipeg Treaty One territory kind of meeting, and maybe we should just just take a moment to reflect on the fact that all across the country we're all working and living in spaces that constitute Turtle Island in its traditional and historic context with First Nations, Inuit, and Métis communities. So today's talk, I hope to review, explore, and turn off my phone. Oh, you'll all be pleased to know that the dog food is in the pet food store. We'll explore how studies' objectives, endpoints, and design decisions shape the analysis, and that's sort of the overriding approach we'll take today. Talk a little bit about intercurrent events, and I wanted to sneak that in. It's one of the newer things that's going on in the clinical trial space, the sort of formal way of thinking about intercurrent events as part of the estimand framework. I know that was the focus of my talk, broadly speaking, the focus of my talk last year, but we'll sneak it in again a little bit this year and highlight the value of involving statistical expertise early and throughout the trial life cycle. In fact, I could probably stop right now because that's really the punchline of the whole thing. So I poked around a little bit in the literature, and this was, I don't think I could have said this much better. So oh dear, George, Gerald, lost the first name of the statistician who wrote this paper in 2010, but he said statistics are an integral part of clinical trials. Elements of the statistical plan, elements of statistics span the clinical trial design, data monitoring, analyses and reporting, and a solid understanding of statistical concepts by clinicians improves the comprehension and resulting quality of clinical trials. I mean, there you are. That's why we're here. We're hoping to raise the bar a little bit through by having to hobnob with I'm sorry, the boring trial statisticians. So one kind of extreme idea in this space is that if your experiment needs statistics, you ought to have done a better experiment, and that's a famous quote from Rutherford, and a bit extreme. But I like to keep that in mind. One of my goals is always to design a trial in which the analysis and the result are just sort of obvious. It's, you know, the biocular trauma test is one of my favorites. If it doesn't jump out and hit you between the eyes, it might be a little more subtle than you hoped. And maybe more relevant for today is the idea that you can't fix by analysis what you bungled by design. And that was a quote from the preface to a book by Leitsinger and Willett in 1990. And so today's goal is to connect trial design decisions to the statistical ideas behind them, and just remind you that they come out of I mean, statisticians sort of grab on and claim them, but they really are just good scientific principles. And we've you know, the statisticians have just sort of grabbed on and given them names. So starting point, a trial is a set of questions, and one of the most important things you can do is establish what is your primary question. And that, the importance of the primary question is really essential to, it's the if a jacket is built off of the shoulders in men's clothing, then the primary question is the shoulders. It's what everything else should hang off of. And secondary and exploratory questions should be designed to support the primary question. And once you've established what those key questions are, the rest of it should flow from those. And those key questions should embody what you've decided are the objectives of the trial. So designing, and having established what those questions are, all the confirmatory analyses have to trace back to those questions. And I'll just momentarily, we'll distinguish between confirmatory analyses, the planned confirmatory analyses from unplanned and hypothesis generating analyses. It's always good fun to look in the data after the data have been collected and think about other questions that might have been addressed, or it might be possible to address in a data set, those sort of secondary use analyses or unplanned analyses at the end of the original trial, just adding things that you didn't anticipate were going to be interesting to follow up on, and now they are. Provided you characterize those as hypothesis generating, you're in good company there, and but you just have to be cautious not to imply that what you've done is confirming results that were posed in advance of the trial. Those a priori things are the reason for doing the trial, and like I say, the objectives shape your primary and secondary and exploratory questions, and then beyond that, it all hangs off. So establishing the objectives. What is the question? What are you trying to show with this trial? Is it a comparison of different treatment strategies? Is it an estimate of the effect of the treatment? And that, though those two sound similar, we'll distinguish them a little bit more carefully later on. And then how does something change over time? The clinical phenomena that we're looking at are we investigating the changes over time? Those different objectives will point towards different endpoints for the study, different designs, and ultimately to different analyses. And please, if I say something that makes you think and you wish to bring it to the group, please, I'm happy to be interrupted. And though I've got a set of slides, I'm okay going off piste regularly. So please do interrupt if it's relevant, if you think it might be relevant. So the idea is to start with the objective. And if your objective is about strategies, then you're going to be looking at something like treatment policy analyses or intention to treat frameworks. Those are the kinds of statistical or terms that are being bandied about. If you're trying to estimate effects, then you might be thinking about hypothetical strategies and heading towards causal contrasts and working with adjusted models because you want to establish what is the biological, what is the true estimate of how much this intervention can change outcomes. And changes over time, you'll probably get into things like mixed models and repeated measures and slope or trajectory estimates. And that's where things can get, statistically, the machinery can get a little bit more bumpy and more bells and whistles attached to it. But those are elegant and appropriate for examining patterns of change over time and differences in patterns of change over time between groups. So things like, are we asking what should clinicians do? What does the drug do? Or how do things change over time? That's what's going to shape our what type of objective we have, and downstream of that, what kind of analysis we're likely to get into. So first off, objectives will shape what our endpoints are. And in the language of the ICH guidelines, endpoints must be relevant, easy to measure, and clinically meaningful. And there's several different kinds of endpoints. And of course, you'll be familiar with these ideas, but did something happen? That's a binary endpoint, yes or no. Did something happen during the conduct of the trial, during the follow-up on the patient? Ordinal outcomes, how bad was it? And characterizing the things that might be associated with how bad the event was. Continuous outcomes, how much did the endpoint change from initiation to completion of the trial, or comparing the averages between groups? Those are the kinds of things of continuous measurements. And time to event, how long until that event happened? It's not just about whether or not it did happen, it's about how long until it happened. So if you've started to think about those types of endpoints, the next step is to be extremely clear about what those endpoints do. They're made up of, what are we measuring? What's the variable? What is the definition of the variable? And sometimes that might be, maybe think of that as, is this going to be a quantified through an ELISA? Is it going to be the clinical assay that's been used 100 years? Is it the first of any possible negative clinical symptom, that there's sign or symptom that turns up? Those kinds of things. Then the timing at which that will be assessed, and the context in which it's assessed. So all of those things are necessary to come up with a clear endpoint to a trial. And that's, we want to sort of distinguish an endpoint from the outcome. And I say, we want to distinguish. For years, I've been trying to sort out, when I'm helping people write up their protocols and their proposals and their protocols and their stats plans, what's the endpoint? What's an objective? Sorry, what's an outcome? What's an endpoint? What's a measurement? What's a variable? And the language of the ICH documents is pretty clear about the idea that the endpoint is the thing that's being measured with all of these details assessed. The outcome is what happens to the patient. And it's not as formally laid out in the ICH documentation. Variable and endpoint are used more formally in that context. But the patient died is an outcome, but mortality measured, assessed on a group of patients, that's the endpoint that we're looking at. Okay, so things like change from baseline in systolic blood pressure at week 12, that's a well-defined endpoint. The HbA1c at month 6 post-randomization, another clear definition of an endpoint. And time to first relapse following treatment, again, a nice, clear assessment of what's going on, a clear definition of an endpoint. Okay, and they're participant level data, and again, outcomes are that the word outcome sometimes bubbles up and becomes associated with the outcome of the trial as a success or failure, or the measured outcome, like the hazard ratio comparing the two treatment arms. I think that's one of the difficulties of the term outcome. It can mean different things, whereas the variable and endpoint are being more carefully handled in the sort of formal clinical trial literature. All right, so again, just the types of endpoints and how, again, how those endpoints, which have been chosen to reflect the outcomes, the objectives, how those endpoints will have impacts on the kind of how they're related to the question, and in a moment how they're related to types of analyses. So if we're asking how often did something happen, then so that you can compare the risks, you're probably talking about a binary endpoint. An ordinal endpoint addresses the question of, did the distribution of severity shift towards milder or more severe outcomes? If the outcome is about the average lab value differing between the groups, then you're talking about a continuous variable. And how quickly did the event occur, or how long did patients last before they had the event? That's you're talking about comparing the timing distribution, time to event kind of analysis, variable, and ultimately those binary, ordinal, continuous, and time to event analyses, endpoints will connect to lead naturally towards typical analyses, and the types of conclusions will reflect that back then on the objectives of the study. So if you've got a binary outcome, you will probably end up doing something like logistic regression, measuring odds ratios or risk ratios, risk differences. If it's an ordinal outcome, such as the severity of an adverse outcome, then you'll be looking at something referred to as the proportional odds model, not seen quite as often, but becoming more and more common in the literature. And that's a generalization of the logistic regression model, in which you recognize that we don't just have a binary outcome, we have an outcome that can take on several different levels. You could even say that the logistic regression is a special case of the proportional odds regression. And the analysis is a nice one in that the ordered categories will have more nuance. They capture more richer statistical info than just, yes, there was an adverse event, or no, there was not an adverse event. Things like post-transfusion change in hemoglobin, nicely addressed by things like linear models and analysis of covariance. In the context of a longitudinal pattern, you remember one of the endpoints, one of the objectives might be about changes over time. Those might be linear mixed effects models, or analysis of covariance, repeated measures approaches, where we're capturing the magnitude of the effect with high sensitivity using a continuous outcome, and these models which focus exactly on those outcomes, those endpoints. And time to event, things like time to next transfusion. You will all have seen many Kaplan-Meier curves and Cox models in our readings. And the advantage of those analyses is that they handle censoring. So that if a patient has been followed throughout the entire trial, and the event of interest has not occurred, the outcome has not occurred, the time to event variable is they made it all the way to 12 months. They had not experienced the outcome, the primary endpoint of the trial. So we will characterize their time to event as 12 months, but note that it is censored, and that censoring is then appropriately handled by the estimates of the hazard ratio in a Cox model. All right, so different objectives lead to different endpoints. Different endpoints are naturally attached to different types of analyses. Likewise, different objectives are supported by different designs. So if you, depending on the type of objective, you'll see different statistical designs in play. And what do we mean by the design? That's how are we going to do the trial? And one of the, apparently I have trouble spelling still. One of the phrases that popped into my head years ago is when I was learning about randomized experiments in general, is that you control what you can and you randomize the rest. And that's sort of the central idea of statistical design. What can we control? What should we control? And we'll use randomization to eliminate or reduce the impact of the possibility of bias in the trial, and control for all the others to reduce unwanted, uncontrolled variation, the noise in the system, to allow us to have a better chance of identifying the effects of interest. Sort of increasing the signal to noise ratio by reducing the noise. And stratified randomization is one of the strongest techniques for that approach. And one of the confusions that can come up when you're talking about statistical design is that we'll use terms like stratification and blocking. Statisticians are comfortable with those when we've learned about them in the context of randomized experiments in general, but they can get a little conflated when we're talking about the design of a study. So stratification is the idea of forming participants into sets, into distinct groups, which are distinct. They're different. We're interested in subgroups, and we want to see balance of the subgroups, with balance of the treatment assigned within those subgroups. And then blocking is a way to ensure that within a set of patients who are otherwise very similar, the only thing that varies is the treatment that's assigned. So blocking is forming participants into blocks that are homogeneous, and stratification is forming patients into subgroups that are heterogeneous. Subgrouping stratification variables are usually interesting, and most statisticians would say should be included in any analyses. Forming participants into blocks to help ensure balance within these subgroups of patients, that's usually just a sort of a part of the mechanism of randomization and is usually left out of analytic plans. So just a subtlety there that has I've had many conversations over the years about those two ideas. Okay, now having established that we've got a design and we've got an endpoint, well, we're back to that idea of the estimand as a way to sharpen the focus on what we've learned by establishing those two things, the design and the endpoint. They give us the estimand, which that ICH E9 R1 document, the addendum on estimands, the estimand framework, says that an estimand is a precise description of the treatment effect which reflects the clinical question posed by a given clinical trial objective. And as we've seen, endpoints and design and objectives and all those things come together. The estimand is often, once we sort of work our way down to that, often it's having established what the estimand is, the rest of the study just sort of falls into place. And the estimand is not a measurement per se. It's certainly not measured at the level of the patient. It's a study level target quantity. And we'll try to estimate that estimand at the end of the study. We'll use an analysis that is designed to give us the best possible estimate of the estimand. And it comprises 5 distinct attributes. And some of these, a lot of this will overlap with what many people have learned as the PICO framework: the population, the intervention, the control, and the outcome. And the estimand framework says that we need to specify the population in which we're conducting the work, the treatment, the definition of the treatment, the intervention, and the control. The endpoint, or the variable, is the thing that will be measured and then summarized. And the intercurrent event strategy, and I want to touch on that a bit more in a moment. And then the summary measure. So the estimand encapsulates all of those ideas, and in a way, it is the thing that is going to be the distilled gold nugget at the end of the mining operation that is a clinical trial. That estimand is really where the everything comes together. So the estimand might be, for example, a mean difference in the week 12 systolic blood pressure under a treatment policy strategy for rescue medication. So it talks about the treatment policy has a lot to do with how we're going to handle things like the patient stop taking their meds, they switch their meds. The mean difference is the statistic that will be calculated to make the comparison of the endpoint that we've measured. And for rescue medication is talking about the treatment that was applied. So the only piece we haven't said there is the population. And as we know, the population is essentially carved out. We might have had a target population when we were thinking up the goal of the trial, the objectives of the trial. But as we start to narrow those down by establishing the inclusion and exclusion criteria, the eligibility criteria, they define the population that we're actually studying. And the hazard ratio, another example would be the hazard ratio. That's the statistic for the time to relapse. There's the endpoint that's measured. Had everyone adhered to the treatment, and that's a hypothetical strategy for how are we going to deal with patients who have stopped taking their meds, switched their meds, they've had an adverse event that caused them to be withdrawn from the trial. In that case, then we're going to talk about a hypothetical strategy had everyone adhered to treatment. And those are, for example, two different ways that we could think about analyze these two strategies. Are two of the strategies that are appropriate and become relevant when we're talking about how are we going to handle intercurrent events in our analyses. So in short, the endpoint is what you measure, and the estimand is what treatment effect you want to learn. So really, that's the point of the whole operation. We're trying to get an estimate of a treatment effect. And the treatment effect comes with all of those things: the population, what are the treatments being compared, the endpoint that's being measured, how are we dealing with the intercurrent events, and how are we summarizing that into a statistical quantity. Okay, so intercurrent events are those things that happen after treatment initiation that could affect the interpretation or even the existence of the endpoint. Okay, and that covers a whole lot of evil things that can occur during a trial. They really, as we think about them, it becomes obvious that they really do matter, and they really alter. If the way we decide to handle them will alter the way that our question is being answered. They'll really change the question if we're not careful. So treatment discontinuation, switching treatments, rescue medication, even death, intercurrent events that change our understanding of what has happened to this patient. They really fundamentally require us to think carefully about how they have changed the interpretation of the data from that patient. And how you deal with them can change the question of the analysis. And the saying is that the intercurrent events reveal your real estimand. The way you decide to analyze them, the way you decide to deal with them in your analysis is going to reveal what you're really working with. Okay, so the strategies that have been characterized for handling intercurrent events, there's four major ones. And one is the treatment policy approach, which very close in spirit to what has been called the intention to treat policy, or the intention to treat approach to clinical trials, which allows or includes everything, regardless of what happens. So that's the sort of, no matter what happens, we're going to count the patient, and we're going to interpret the results that we got from that patient. There's other types of intercurrent event strategies where we might want to fold that intercurrent event into the definition of the endpoint, right? So, for example, if a patient has had a transfusion, and we're hoping to see that the patient has had a healthy outcome at following that, the need for rescue med might be one of the things that we want to characterize as an intercurrent event. It would be an intercurrent event, and we'd want to anticipate how we're going to handle that. And rather than talking about time to discharge from hospital or the need for rescue med, or time to readmission into the ICU or time to rescue med. Those, maybe we want to fold those two ideas, the return to ICU or the rescue med, as two ways of establishing the endpoint of the negative outcome following the transfusion. There's also the hypothetical framework. That's where we imagine that the intercurrent event did not occur, and that starts to get all of these ideas are, I think, have risen to prominence over the past 10, 15 years, in parallel with the rise of causal, what's been known in the statistical and other literatures as causal inference, where we try to think about establishing more carefully what it is that we're trying to estimate and what those things mean. And one of the tools is counterfactuals. And if you've done any thinking in the reading in the causal inference literature, the idea of the counterfactual and establishing what would have happened had we done something different for this individual is the sort of the heart of the counterfactual modeling. And those allow us to explore hypothetical treatment strategies or hypothetical decisions that might be made for the patients. And the idea of the principal stratum analysis, where we focus on subgroups that are defined by the counterfactual occurrence or non-occurrence of the intercurrent event. And that mouthful, I have to admit, is still on my list of things that I need to absorb and get more deeply into it. If others here are more comfortable describing what the principal stratum approach in handling intercurrent event, whoop, there we are. I hope my screen didn't just flash on and off for you folks. If the distinction amongst these four strategies is of interest to you, chat with a statistician, particularly one who's more familiar with the principal stratum approach. But the ICH E9R1 document lays these out in great detail. Okay, so having gone from the overall objectives of the trial and letting them shape the way we establish the endpoints and the way that we think about the design, those two things come together and help us understand the estimand that's in play. From the estimand, it's a short hop, skip, and a jump to the analyses that are going to be needed. And those choices really lock in the analysis. And so we start with the idea of the objectives, shaping both the endpoints and the design. They come together to create the specification of the estimand, and it's almost implicit what will be the appropriate analysis method, having established all of the above. So if you need a roadmap to help you navigate through clinical trials and your interactions with statisticians about clinical trials, if you came to me with an understanding of or at least an initial idea of how your objectives shape your endpoints and your design that you're thinking of adopting, and the way that those will characterize into an estimand and the analytic method, I would think that my stars have aligned, and the clients, these much of the hard work will have already been done. And at that point, I just need to sort of help you review through those processes, maybe help you tighten up or update your objectives. We go through the question of what it is that you're going to measure on the patients, how you're going to measure them, what's the statistical design. Those come together. We sort of review and confirm that the estimand speaks directly to the objectives you had when you were laying out the trial. And from the estimand, we review the appropriate collection of analytic methods that might be available. So having thought through that kind of roadmap, our course will be quite clear from that point forward. So that was the main meat and potatoes of what I hope to review today. And I get that it's lots and lots of details there, and I realize it probably feels a little bit like I've sort of said, here's how you might consider getting yourself into shape after not being at the gym for a number of years. But if you are considering doing these, you should talk to a medical professional and make sure that the exercise program that we're going to discuss is appropriate to you. I feel a little bit like I just said, talk to a statistician if what you are or the so that these design concepts and analysis proposals, see if they're really appropriate for your situation. We've got a common language established through the Estiman framework and the series of steps that we've just discussed, which will make our discussions much more focused and concrete. But there are many other details in there that we would want to consider. And I thought I'll just sort of touch on a few of those so that they're fresh in your mind as you're putting together your own thoughts on the trials that you might be proposing. So other considerations, for example, things like, is this a superiority or a non-inferiority kind of question, right? And if the objective that you're hoping to establish is that intervention A is better than intervention B, then one of then you're probably operating in the space of a superiority trial, and those are commonly used. The most clinical trials that we read about in the literature are framed as a demonstration of superiority. For the approval of a new drug, for example, demonstrate that a more effective treatment option is available. And one of the key parts of the discussion that comes up when we're planning is, what's the effect size, which will help us establish what is the appropriate sample size that's going to be in play. But the effect size in this case is going to be about what's the smallest difference in the thing that we're going to measure, the estimand, that is clinically important. If we can establish what is the smallest clinically important difference, the MCID, then we'll have most of the information we need in order to evaluate a sample size. And that smallest clinically important difference is both extremely challenging and often many people have learned about sample size calculations through the ideas of sort of Cohen's d. What's the effect size? Is it small, medium, or large? And in a way that I've always felt that was a total cop-out. It's one that you sometimes have to embrace when there's very little information available, or if you were thinking about this as a sort of practical feasibility trial. Can we conduct this? But can we implement this protocol? Can we recruit the patients? Will we be able to do a larger study? Establishing the minimum clinically important difference in a context like that is often very hard, and something like a small, medium, large effect sizes and the required sample sizes for those, it can be helpful, sure. But establishing that a trial would be done if the difference is this big, and sorry, I'm now using my hands in the little picture, but the difference is this big, and we would not be all that excited if the difference was smaller than that. That's the number that we need to establish. That's the number that will tell us whether the trial is being planned to find the thing that is going to make a difference. And anything bigger than that would be great. Anything smaller than that, and even if we established it carefully, it would be so small that nobody would be very interested in that. It would not lead to change in clinical practice, for example, or it would just be not worth proceeding further down the pipeline. So that effect size, the minimum clinically important difference, one of the key characteristics of a superiority trial. In a non-inferiority trial, the role of the null and the alternative, and I've avoided getting into hypotheses very deeply, but that language of null and alternative hypotheses have almost flipped. In a non-inferiority trial, our goal is to show that intervention A is not worse than B. It's not inferior to B. And that's usually in the context of something like the new option A, intervention A, is a cheaper or safer alternative than B. And we want to demonstrate that it's just as good as, or close enough for government work. And that idea of A being not worse than B. Okay, and famously in the bioequivalent study of generics, right? There's an equivalence margin of 0.8 to 1.2 on the effect size, something like that in a bioequivalent study of a generic product versus the approved earlier in class products that have been given market approval. Okay, and one of the where the effect size, the minimum clinically important difference, is one of the key ideas, numerical ideas associated with a superiority trial. The non-inferiority margin, how close is close enough, is critical to the planning of a non-inferiority trial. And that, so the non-inferiority margin, if you've ever wrestled with a statistician about establishing your minimum clinically important difference and tried to get your colleagues to agree on what the minimum clinically important difference is going to be, the delta for a superiority trial, it will be that much more exciting to try to get them to agree on what is the non-inferiority margin. How close is close enough? And there's a kind of a famous cartoon that shows up at this or in very minor variations, where the primary tool for establishing non-inferiority usually boils down to effectively a confidence interval, and the width, the location of the confidence interval and its endpoints are usually used as the basis of the statistical evaluation at the end of the trial. So if your confidence interval for the effect size is a negative number, there's 0, where there's no difference between for example, the probability of a clinical, so this is a negative. So the probability of a positive outcome is negative here. It's being estimated to be negative, but our study was a little bit imprecise, and it ranged the confidence interval for that difference in proportions is ranging from a very large clinically inferior result to a clinically non-inferior result, and that range that it falls outside the confidence interval includes the non-inferiority margin, suggests that what we're talking about is a non-inferior result. And if the point estimate happens to be on the left-hand side of the non-inferiority margin, but the confidence interval still permits that it's quite reasonable to say that the effect could be in the non-inferiority region, then we would need to say that the clinical non-inferiority has not been established. Only in the case of the entire confidence interval being to the left of the non-inferiority margin would we say that we have demonstrated non-inferiority in this outcome. Now, strangely, you can end up with situations where there are conclusions of superiority, but also non-inferiority. And that's where, for example, where the confidence interval for the effect doesn't include 0, we have demonstrated a statistically significant treatment effect, if you will, but it is not so big that our confidence interval is not so far to the left that we can rule out that it actually is the improvement is not sufficient to get it out of the non-inferior range, which is a crazy making conclusion which occasionally occurs, and other times where you end up demonstrating that the product is actually superior, and we happily conclude that we have shown superiority. Though if that is not the planned objective of the trial, that result is often couched in sort of a careful terms to say that, look, this wasn't intended as a superiority trial, a non-inferiority trial, though we have demonstrated superiority through the conduct. So non-inferiority trials are they can make your head hurt. They make mine hurt at least. And one of the best accessible papers, I think, in that space is the one by a colleague I have a great respect for, Janet Wittes, in 2011, and the paper is called "Through the Looking Glass," and it really does that title really does capture the sort of through the looking glass feeling of a experienced trialists who are used to null and alternative hypotheses having a certain relationship, and we end up flipping them, and it can be well, that's nicely explained and discussed in that paper. And the FDA in 2016 did come out with a formal guidance document on non-inferiority clinical trials. Okay, so non-inferiority versus superiority is an important thing to recognize. One of the questions that I'm often asked about in conducting analyses, the planning analyses for clinical trials, is whether or not we should be adjusting for covariate. And here's the path that I usually go through that. We randomized the treatment assignment. We randomized it carefully. It was well blinded. So the statisticians are comfortable saying that no biases are expected. Right? We trust that what we've done is going to create a fair comparison of the two or more arms. However, there could be residual biases that can creep in, but that's not sufficient to justify including a covariate. If the covariate is being included simply to reduce possible bias, that's not a great argument to include it. However, if you have planned and relevant covariates, that including them will only be helpful to the extent that they explain what would otherwise be noise, giving you greater power in your analysis. That signal to noise ratio, which is usually the core of a statistical comparison, that signal to noise ratio will be more sensitive when you reduce the noise in the denominator. So do include covariates that reflect how the randomization was stratified. And randomization is stratification of the randomization is definitely going to lead to planned and relevant covariates that should be included in the model. And I was raised that as thou hast randomized, thou shalt analyze. And so that idea that the way that you conducted your randomization is going to have an immediate and direct impact on the statistical modeling that you do is baked into my training. And including planned and relevant covariates will almost certainly improve the power of your analysis. And this I include because when you're doing sample size calculations, it can be extremely challenging to come up with good understanding of how much impact will come from including planned and relevant covariates. However, in some more straightforward circumstances, it's possible to characterize in a sort of sensitivity analysis. If the covariate is this strong, how much impact will it have? If the covariate is even stronger, it will increase the power even more. But the idea that if you do an analysis, if you plan an analysis that will be based on planned relevant covariates, such as those on which you have done stratification, your sample size calculations that ignore these covariates will almost certainly be considered conservative, right? So you can essentially, you can do your sample size calculation as though you anticipate doing only as simple as a two-sample t-test, even though you plan on including age, categories, and sex as covariates in the model, because that's how you plan to do your randomization. If you do that, then your sample size that's established by the sort of grinding through the calculations for a simple t-test will almost certainly be conservative. You will almost certainly improve your power by having included the age and sex on which you did your randomization. Okay, sorry, on which you stratified your randomization. Now, you can also include other covariates. Maybe they're covariates that you know will be linked strongly to the outcomes. They won't be linked strongly to the treatment that was assigned because we did randomization. If clinical condition at the start of the study is an important predictor of how they will do over the course of the study, but you don't feel that you can stratify on the basis of clinical condition, including clinical condition as a covariate in the analysis will almost certainly improve the power, but that's only to the extent that they actually explain what would otherwise be noise. Okay, but you should include the planned covariates, those covariates on which you did your stratification. Okay, so adjusting for covariates, it's kind of a high level approach to that, and it's particularly relevant because so many statistical analyses will depend on regression models of one flavor or another. So it's often relevant. And one last sort of high-level thing, Bayesian inference becoming extremely, well, an interest of mine, though I have to admit that I'm still in the stage of an enthusiastic student of the approach, but they're certainly becoming more common. Just this January, the FDA came out with a guidance document called The Use of Bayesian Methodology in Clinical Trials of Drug and Biological Products. It's a mouthful, but the fact that there's now a guidance document that's fully published tells you that with the methodology is coming of age in the clinical trial space. And it's been common in academic and device trials for a number of years. So it's really out there and being used. And in my opinion, and I say that with the humility of I truly am a student more than an expert. The Bayesian approach provides a much more it provides a more principled answer to the questions of interest to clinicians and patients. So contrast the idea that in a Bayesian analysis, the question that you might be able to answer at the end, that you hope to answer, is what's the probability that this intervention will improve the outcome for me or my patient? What's the probability that the intervention works? And that's versus the language that emerges from a frequentist analysis, which is what's the probability we might see results as good as or better than we saw in this trial if there really is no benefit to the treatment and we were to do this trial again many times. So there's an awful lot going on in that statement, and it's one that I'm having a harder and harder time advocating for in my approach to conducting clinical trials, though I have to admit to a great deal of intellectual laziness, I suppose. Frequentist methods are the methods that I was trained in. They're the methods I've used for years and years. So I do tend to sort of start with those, and then I overlay the possibility of a Bayesian approach to these things and look for opportunities to continue my own learning. But I really do believe that this is by far the more relevant question to address in a clinical trial than this one. Okay, so statisticians, talk to them early, talk to them often, and earlier than you might think. As you are developing the protocol, let us get involved as you think about your objectives. Let us help you, let us use us as a sounding board for expressing, for characterizing your objectives, and that will then prime us to help you establish the endpoints, choose a design. It sets us up so well to work with you in establishing what are the intercurrent events that we need to be aware of and how should they enter into our notion of the estimand. And if we've had those conversations in advance of as we construct the protocol with you, analysis planning almost falls into your lap. The care with which we go through these earlier pieces leads to an effective analysis plan and far fewer headaches later on. I don't know how many trials I've been involved in which what I now would call an intercurrent event becomes the major stumbling block to understanding how we should best address an analysis. And if you're struggling to figure out how to address the analysis at the end of the trial, your results are going to come with a great deal, they're going to be viewed with a great deal more skepticism than if you had established exactly what the intercurrent events of interest were likely to be and how you were going to incorporate those in your estimate and ultimately into the analyses. So get us involved early, prime the pumps, things will flow more smoothly. Okay. And if you approach a statistician late in the process, we often end up retrofitting analyses, adapting to choices that could have been avoided. And that could lead to awkward endpoints, missing data that we might have been able to prevent, or analysis methods that just feel forced, generating that skepticism in the community. Early collaboration avoids those, can help avoid protocol amendments, delays, and frustration. So retrofit analyses and avoidable protocol amendments, endpoints that don't answer the real question, and ultimately trials that never really had a fair chance at success. So talk to the statisticians early. And what are some of the easy ways to engage with a statistician? Make those early consultations short. They don't have to be 3-hour marathons. chat up a statistician in the elevator as you're heading up to your office, dangle the idea of getting them involved in the statistical in the planning of your protocol. Most statisticians will eagerly grab at the opportunity to get involved early. We know that the value. Ask your dumb questions so they have the opportunity, the space to ask their dumb questions. So don't be afraid to ask, what do you mean by intercurrent event? Which is not a dumb question. Which will give me the opportunity to say, hold on, what do you mean seizures? Is a seizure something that we really do need to define carefully, or is it well understood in your literature? Argue through the key design element points and reconnect with the statistician as you establish deeper and deeper into that roadmap. It's not going to be solved in one, it's certainly not going to be solved in the elevator up to the office or in that first 1 hour consult. But after a series of consultations where you've gotten to know each other, you've learned each other's language, the results will be stronger than if we had not had the chance to chat. And this is a pretty famous experiment, and it does a nice job of explaining the cost of a late stage stats consult. To call in the statistician after the experiment is done is like asking a physician to do a postmortem. You might be able to say why the experiment died. And Ronald Fisher is the sort of source of that. And though he's famous as a geneticist and mathematician, he's one of the, I'll say, fathers of modern statistics. He was also a eugenicist, and he became a paid shill for the tobacco industry in his later years. And he's probably a real jerk based on some of the conversations he had in the literature and at stats meetings with other statisticians. But it is a good line. So it's one of my favorites. All right, just to wrap up then, start with the objectives. They will tell you about the endpoints and the design, and from those, the analysis is essentially already determined. Consider the role of intercurrent events in how they're going to shape the meaning of your results and plan for them, and partner with a statistician early to save headaches later on. So thank you very much. I think I'm probably top of the hour, so I don't know that we've got time for many questions, but I'm happy to chat and stick around for a bit.
Thank you so much, Robin. Before we open it up for questions, I think we've got time for maybe a couple. Just want to emphasize this was perfectly keyed for the purpose of this lecture series, which is helping non-statisticians design their trials. So thank you so much for such a fantastic overview. Do we have any questions or comments?
Rob, it's Ryan here. I could ask a question if there's opportunity to do that. I know we're running out of time. You talked a little bit about stratification, and I feel like, that's like a good go-to, but like for small trials or even for like larger ones where we want to stratify. Like, I find that investigators, including myself, want to stratify for more things than we should, because we end up with these small cells, and it can easily create for enrollment issues, but also imbalances. What about using like covariate adaptive like randomization? Like, what do you think of that? And should we like advantages or disadvantages? It's something I'm toying with using more in trials going
Yeah,
forward.
Ryan, thank you. The idea of a covariate adaptive randomization, I'm sorry, there's a bunch of different terms in there, and they get mixed and matched in different ways. But the
Yeah.
sort of hey, if we only had to stratify by sex, so that within the males we had 50-50 treatment and control, within the females we had 50-50 treatment and control. Oh, but we also want to consider sites. We also want to consider age groups. Oh, and I suppose we need to talk about etiology. Oh my God, and we also have to.
Yeah, this is where we're at with trials. Everyone wants to do this, and
Exactly.
then they end up with like 6 cells in each side. And I'm trying to figure out how to avoid this
Yeah.
for Alexi and myself and for many others.
Yeah, as the cells as the expected cell sizes dwindle, and as you end up with anticipating that many of the cells are going to end up being empty. I mean, it's a natural consequence of the clinical space in which the trial is being conducted. Maybe there just aren't that many patients that will fall into that cell, and that's not to say that you can't conduct the randomization that way. All you're really saying is that in each of those cells, we're going to try to make sure that it's 50-50, which is a very it's a beautiful thing to do from a statistical perspective, but operationally it can get challenging. An alternative approach is to construct a kind of a score which addresses, so how out of balance are we now in these key characteristics that we want to achieve balance in age and sex and etiology. How many, there's far too many cells, but we could probably keep our an eye on how imbalanced things are. And every time we look at a new patient, we can say, hey, I know which cell that patient would fall in. And if I put them in this group, this treatment arm or into that treatment arm, which one is going to bring us back into balance most effectively? And then when you do your randomization, you randomize in such a way so that it's more likely that the patient will end up being assigned to the treatment arm, which will bring things back into balance most effectively. So it's a lovely approach. Operationally, a little challenging because it means that establishing the criteria and having that criteria measured and available as you essentially do the randomization, it operationally can be tricky, but it's an alternative that has creates a nice compromise between just letting randomization take care of it in the long run versus over stratifying and creating cells that are too small to be operational.
Yeah. Thanks.
Okay, and I am afraid we are out of time, but fantastic. Thank you again, Rob, and for everyone for participating in today's session. I will just quickly pull up just the schedule to show that we are meeting again next on March 19th, where Julia Abelson will be speaking about patient and community engagement in trial design and conduct. Okay, thanks everyone.
Okay, thank you.